It's really nice to be here. Ghent is amazing, and it's really nice to all the excitement. Actually, I thought of entering the stage like this because I was one of the 3 survivors from QIP. Okay, so this is about a new result with Xun Gao and Zeph Landau, Yunchao Liu, and Umesh Vazirani. And basically, it's about an algorithm for polynomial-time classical, a polynomial-time classical algorithm for simulating noisy quantum circuits, or about the random circuit sampling experiments. But more generally, it's about testing quantum advantage. So just to start from the beginning, basically a cornerstone that has underlined theoretical computer science for a long time, even before it was formally stated, is the extended Church-Turing thesis, formally stated by Bernstein and Vazirani in '93, that says that all physically realizable computational models can be simulated in polynomial time by a probabilistic Turing machine. And why is this so important? Basically, it's important because it tells us that the complexity of various problems does not depend on the exact details of the model. It gives some kind of a universality to all types of computational models. Enter quantum computers, and basically we very strongly believe, and this is why the number of people grows exponentially in this field, that quantum computers should or could violate the extended Church-Turing thesis. And maybe it's worthwhile to pinpoint exactly what underlies this belief. It essentially can be divided to 2 beliefs. One is a mathematical conjecture that BQP is strictly larger than BBP. And I think there's no real doubt about that. And the second is that quantum systems can, in principle, physically implement BQP. And this is maybe more doubtful. The belief relies very strongly on the notion of quantum error correcting codes and the fault tolerance theorem, or the threshold theorem. But the question, I think it's very worthwhile asking what are the underlying principles of this belief, and maybe just to stress how strong this belief is, or how sort of mind-boggling this belief is. Basically, it says that there is a different, one can view this as if there's a different phase of matter in fault tolerance. When we reach quantum fault tolerance, basically we expect to have some kind of quantum universality exhibited by all these different quantum systems, which are going to be truly quantum, or truly quantum universal. And so we believe that this quantum universality is very different from classical universality, in that it can actually allow physical systems to exhibit macroscopic entanglement in a controlled way, and that a wide class of quantum systems can exhibit this quantum universality, and that it's very different than classical universality, almost like water and ice. And this picture of a phase transition actually was studied by me a long time ago. You can look at it as a phase transition. But the point is that these two different types of behaviors are extremely different, and even remarkable experiments like Kotler et al. Experiment, which won the Breakthrough of the Year by Physics World in 2021, this only gives macroscopic entanglement between a few degrees of freedom. So the entanglement is not so complex, even though it's macroscopic. We're talking about something completely different. Okay, so I think it's worthwhile understanding what evidence do we have for this belief. And I came across this question. So just to say, we are all, I think, here because we very strongly believe this, and because essentially the scientific world believes this. So I think I came across this question of whether whether it's a valid or whether it's whether we should believe it, in a conversation with two prominent computer scientists, Oded Goldreich and Madhu Sudan, in 2004. And I had a very sort of lively discussion with them, and I was very enthusiastic about quantum computation, and told them, obviously, this is you know, it's very. Look, quantum systems are so hard to simulate, and obviously this is there's no reason to doubt this, and basically the result of this conversation, well, at that time I was trying to come up with evidence for them, and I couldn't, and the result of this conversation was for me some kind of a formulation of what is really wanted. What is really the desired thing in order to show this. And of course, it's a soft requirement. It's not a mathematical claim, because nothing about the real world will be a mathematical claim. We cannot really prove that really there is this phase transition, right? Because we live in a finite world. But we want stronger evidence. And so we want a challenge of the following sort: a computational problem that is conjectured to be super polynomially hard for classical computers. Its solution can be verified. And there is good evidence that quantum computers can solve it efficiently for large instances. Okay, and note that I'm really interested here in the evidence for scalable violation of the extended Church-Turing thesis, and not about practical advantage, finite advantage, or just an advantage of having a quantum computer to play with as a physicist that would make it very comfortable. Okay, I'm really interested in the evidence for violation of the extended Church-Turing thesis, experimental violation for the experimental evidence for this violation. Okay, so it seems very hard to give such a scalable, such a evidence for scalable quantum advantage from existing data, and basically I want to give. So the talk outline is going to be, first of all, try to get a little bit deeper into why quantum simulations do not give such evidence. And then go to the result of random circuit sampling, which has been the attempt to give such evidence, and ask, can we show scalable quantum supremacy in this avenue? And then maybe in the last few minutes of my talk, I want to talk about quantum supremacy in the NISQ era in general, what we can hope for. Okay. So you may ask, and rightfully so, simulating many body systems is hard. This has been, quantum simulations have been Feynman's first motivation for quantum computation, whereas Feynman's picture went away. And Sirac and Zoller also argued that noisy quantum computers, noisy quantum systems are easier to simulate by noisy devices, because the noise sort of would simulate the noise in the device. So maybe this is a better candidate for quantum supremacy evidence. And quantum simulations seem to be a really appealing platform for quantum advantage, and it has been studied quite extensively. Universal simulators of 2D systems were found by Qubit, Montanari, and Piddock, and those simulators were efficient for 2D systems, and we extended that for efficient simulations for all connectivities. This field is experimentally thriving, and you can even ask. Isn't even the very fact, forget about quantum simulations, which is the ability to simulate a physical system by a controlled physical system or another physical system, isn't the very fact that quantum mechanics simulates itself already evidence for this, for quantum advantage, because it's so hard to simulate. And this is a survey, a recent excellent survey about practical quantum advantage in quantum simulation. And note the green, I don't know if you can see this. Is it? Yeah. So arguing that a first practical quantum advantage already exists in the case of specialized applications of analog devices. This shows that the language needs to be better clarified. So it's not at all clear. So it seems like these simulations really perform very interesting and impressive things, but it's not clear that they answer this requirement of the challenge, especially because there's no computational problem that is well defined that these simulations perform. And I want to highlight out of these 3 points, 3 sort of requirements, the requirement that its solution can be verified, which makes it even more difficult to come up with such an example. And I challenge you to try to see if you can come up with an example for this for evidence for violation of quantum of the extended Church-Turing thesis via existing experimental results. So I want to highlight this the second point. Its solution can be verified, and maybe there is a reason for the difficulty of satisfying this particular solution, this particular requirement, and this is how one can view quantum general experiments actually. So on the left there is the theoretician who is trying to come up with predictions for a quantum experiment, or to test a physical theory, not a quantum experiment, sorry, an experiment to test a physical theory. And on the right, there is an experimentalist. And in the usual paradigm, predict and compare paradigm, the experimentalist runs the experiment, the theoretician performs the calculations to make the predictions, and then they compare. In quantum many-body physics, this is impossible. This is impossible to do because this prediction is impossible to do because efficient simulations of general many-body dynamics is impossible according to what we think. So this seems to be an inherent difficulty, saying that we cannot efficiently test the high complexity regime in the usual predict and compare paradigm. This has been sort of bypassed and addressed in the whole direction of efficient verification of quantum evolutions, and we now know how to do that in controlled systems, even without even without quantum interactions, just by classical interactions with the beautiful result of Mahadev. But this has not been done with quantum simulations. Okay, it's not been done on it. So some small, simple experimental results where experiments were conducted, and that is really very impressive. But it has not been done for a problem that satisfies these 3 requirements that I talked about. So going back to this challenge, I think quantum simulations have not actually provided us yet with such an example, and I think the difficulty is that well, we can wait for us to for someone to finally implement Shor's algorithm or some other algorithm, and then that would be very strong evidence for such a violation. But we don't want to wait that long. We're working very hard, investing a lot of money on this problem, so on the problem of reaching this quantum advantage. So we might as well have good evidence for why we do that before we do that. And I think the difficulty here is that we're trying to do that in what's called the NISQ era. Okay, and one can ask, do we even expect scalable evaluation of the extended Church-Turing thesis in NISQ systems? And I'll get back to this question later on. Let's see how I'm doing in time. Good. By the way, I like interaction, so I don't know if the organizers are here and allow questions in the middle, but I don't mind. Okay, so the community has focused in the past 10 years on a very important this important task of providing this quantum advantage evidence, and one of the important focuses was random circuit sampling. And so Google claimed in 2019 for this breakthrough of quantum supremacy using this random circuit sampling paradigm. Okay, so what's this paradigm? We want to use current noisy intermediate scale quantum systems to sample from a random quantum circuit. Use a statistical test to evaluate how good the device is performing. Claim that the same performance cannot be achieved classically. And these experiments that were done also by Google and in China on 53 up to 60 qubit experiments were doing that, and they achieved, they're very extremely impressive experiments, great advance in quantum control experiments, and the ability to control quantum systems, and they provide a very important challenge to classical algorithms. But the question is, can these experiments provide evidence for scalable violation of the extended church-sharing thesis? And again, I want to stress that we discuss here only the asymptotics. I'm not talking about finite size advantages. Okay. So let's go a little bit deeper into the paradigm. So this is the random circuit sampling experiments. We have the circuit here with some noise acting on each one of the qubits at a time, IID, with, say the depolarizing noise. And we sample a random circuit C on n qubits with depth d. Sorry, we fix the circuit. We obtain m samples from the noisy distribution p tilde. And then we perform some statistical test. Okay, so we compute a statistical measure, a metric, f, depending on the circuit C, on those m samples. And note that because of the verification problem that I told you about before, of the fact that it's hard to verify highly complex quantum evolutions, let's give up this issue of this complication in verification, or the high complexity of verification, and allow exponential verifications. Okay, this is okay. The fact that the verifications are exponential doesn't mean that we cannot verify these things. It just means that we will have to resort to smaller instances, which is fine. Okay, so allow such exponential time verifications, and maybe you need to repeat this procedure for a few circuits, or for many circuits. Okay, so basically there have been several suggestions for such statistical tests. For example, the cross entropy benchmark written here, where if you look at so this is the sum over Q, with Q of C of X, which is the probability, the outcome probability for a given circuit C to get X, the output X, times some probability of X with respect to some probability distribution P. And the linear cross entropy benchmark fidelity is defined for that particular probability P to be this quantity. And note that for P being the uniform distribution, this is 0. And for a random quantum circuit, this is with high probability very close to 1. And the goal is to sample X from some probability distribution, which achieves this cross-entropy benchmark fidelity larger than an inverse polynomial, larger than a constant, or even larger than an inverse polynomial. Okay, so that is one test that Google paper considered. And for example, there is the heavy output generation test suggested by Aronson and Chen, which I'm not going to define. But I just want to note that the hardness conjectures, the assumption that these tests are really difficult, can be stated as there's no efficient classical algorithm that can pass these tests, And the arguments for hardness rely very strongly on a notion called anti-concentration, which is basically saying that the distribution is well spread. So anti-concentration is this quantity here that takes the expectation over the circuits, according to the probability distribution that we're considering, of the probability of to get to output x squared. And if p is a delta function, then this will be 1, and we want this to be at most order of 1 over 2 to the n. Okay, so this anti-concentration somehow comes into play in all the in the entire field, and in Bill Pfefferman's beautiful survey in the tutorial. I think he gave the history much better than I can get into the details of. But this is a very critical point. Okay, so these hardness assumptions of these tests, or especially of the cross-entropy benchmark test, were, I think it's safe to say that in 2021, already a lot of doubt was cast on these tests by the result of Gao, Kalinowski, Chow, Lukin, Barak, and Choi, where they say basically that one can achieve some kind of violation or some kind of passing this test with better than expected performance. I'm not going to go into the details. I think Bill mentioned that. Where is Bill? You did, right? In your tutorial? Okay, so already some doubt was cast by then, and our main result is basically that this test can be passed by this test, and all other statistical tests for random circuit sampling can be passed by a classical algorithm. Okay, so let me go through the theorem. So assuming anti-concentration, there is a classical algorithm that on input a random circuit C on n qubits outputs a sample from a distribution that is epsilon close to the noisy output distribution P tilde in total variation distance in epsilon close in total variation distance with success probability over the circuits at least 99%, for example. And that simulation runs in time, which is polynomial in n and in 1 over epsilon. Okay, so why does this imply what I just said? Well, assume that the quantum experiment runs m samples and performs some statistical test on them. The claim is that the algorithm will output, or can output, the classical algorithm can output m samples as well. It will take polynomial time, classical polynomial time, polynomial in m and in n, and such that no statistical test can tell the difference with better than some probability. And essentially, this relies on a very basic fact in probability theory that two probability distributions cannot be distinguished by any statistical test on m samples, say with probability 0.51, say with achieving bias 1%. If they're very close in total variation distance, where very close is, say, 1% of this 1 over m. Okay? So you need more than 1 over the distance in total variation distance in order to actually manage to distinguish. Okay, so then given, if you fix the number of samples, m, that is going to be run by the experiment, or by the test, then we, the simulators, will choose epsilon as we want. We can make it inverse polynomial, arbitrarily large with an arbitrarily large polynomial. So we fix epsilon to be, say, 1% of 1 over m, and then we guarantee indistinguishability, and the running time is going to be polynomial in n and m. so efficient in the experiment. Okay, so I want to highlight here the role of the circuit depth. As I said, there is this general, the central assumption of anti-concentration, and it has been shown that anti-concentration requires at least log n depth to achieve. So that means that the depth needs to be at least logarithmic. On the other hand, since noise is acting on the system, and there is no way to pump out entropy, the distance from the distance of the output probability distribution can be shown to decrease to zero exponentially in the depth. So after d layers of the quantum circuit, the output distribution is going to be 2 to the minus d, close to uniform. And since we want the experiment needs at least 2 to the d samples for that to distinguish even from the uniform distribution, well, and since we want this number of samples m to be polynomial, then we must have d less than log n, or O of log n. Okay, so there's a sweet spot here of log n, identified by Deshpande et al. 2021, in which we can actually hope for such simulations to work and provide evidence, for such experiments to work and provide evidence. Okay, good. So this is the sweet spot, and we're going to focus on that. And here is again the theorem. So the running time of our algorithm is polynomial in the running time of the experiment. That's what I said before. And some further remarks is that, first of all, currently our running time is definitely not practical. It's O of the number of samples to the 1 over gamma, where gamma is the noise per gate. So if you think of current numbers, then we're talking about polynomials of degree 1000 or something like that. Okay, that's bad. And also, a very important point is that I want to mention Gao and Duan's beautiful paper from 2018, which this result very strongly relies on in terms of techniques and ideas. And their result implies a simulation in quasi-polynomial time, rather than polynomial. However, this was not known before, essentially because in order to notice that, we needed the fact that anti-concentration is achieved in log depth, which we didn't know at the time. Okay, so the upshot is that we deduced that noisy random circuits, with several caveats which we can talk about later, but overall, it seems like this provides extremely good evidence that random circuit sampling cannot be the basis of a scalable experimental validation of the extended Turing thesis. Okay, so let me go into the proof sketch. How am I doing on time? Okay, good. Okay, so here's the claim again. Yeah, so I want to sketch the approach, and basically let's start from why it's difficult, or why it's considered difficult to perform such a simulation. Well, think of the random circuit, or the circuit, in terms of the Feynman path integral. So the output probability is written as the sandwich of C with zeros on both sides, and we write it as a Feynman path integral. And the intuition for the hardness is that each of these exponentially many paths will contribute the same way. So there are exponentially many of them, so why focus on each one of them? And if you just take polynomially many of them to try to perform a classical simulation, well, then you'll have only exponentially small correlation with the output. So that's not good enough. Okay, so that's why one might conjecture that one actually conjectures that simulating ideal quantum computers is hard. And in this framework, it's not clear, or when we look at it as a Feynman path integral, it's not clear how noise can help us. Okay, so now the first idea is to move to Feynman path in Pauli basis. So you can look at this, how do I move here? Can you see this? Yes. Okay, so let's look at the second line here, okay? I'm moving here from vector basis to operator basis, and I'm writing, instead of the sandwich of the probability, I'm writing the probability squared. And in the second line, I've just written this Feynman path in Pauli basis in double ket notation, which basically just says take a matrix and write it as a vector. Take a superoperator and write it as a matrix. Okay? So then we sum here over all Pauli path, which is basically the ability. So each Pauli here is in the Pauli group of n qubits, and so in each layer of the circuit, I'm sticking such a Pauli operator, and a Pauli path is basically the list of all those Paulis, and we sum over all the Pauli paths, and this is done by basically sticking the projection on the sum of the projections on each one of these Pauli paths, which is the identity in this representation, and you here, the different gates are basically, they basically become the superoperators. Okay, so this is equal to this, to the second line, and the fact that the second line is equal to the first line is easy to see. Maybe I have this here. Yes, so it's easy to see using these this equality. So if you have the Pauli in matrix form mapped by this unitary layer, the UD is the dth layer, well, in vector form, or in operator form, in operator form, it becomes this, okay? So this inner product in the double ket form is simply the trace in the matrix form, okay? So we moved from a vector basis, transition amplitude from I to J is this value, to a Pauli basis, transition amplitude from Pauli to Pauli, which is this trace. Okay. Now note that the way I've written it here, I'm summing over the Pauli path. Where is this red thing? Yes, okay. I'm summing over the Pauli path, and each one of them contributes this term, and I want to call this term the Fourier coefficient for that circuit at that Pauli path. So the probability of the circuit C to output 0 to the n is going to be this sum of Fourier coefficients over all Pauli path S. Okay, good. So why is this useful? This description. Well, the point is that it behaves very nicely when you apply noise to it. And why is that? Well, look at the depolarizing noise, which acts on an operator as 1 minus gamma times this operator plus gamma over 2, the trace of this operator. Well, Paulis have trace 0. So basically, identity goes to identity, but any one of the Pauli operators is going to go to just 1 minus gamma times itself. Okay, so that means things look very nicely in this ideal setting, because noise in the Pauli path integral becomes this really easy to describe effect. You stick in noise in between the unitaries, which means that this noise applies on this Pauli operator for each one of the layers. And what that means is that whereas this is the probability that we're trying to simulate, the ideal probability, this is the probability that we're trying to simulate, which is the P tilde, the noisy probability. And in this probability, we just have a factor of 1 minus gamma to the weight of the Pauli path in front of each Fourier coefficient corresponding to a particular Pauli path. Okay? And this makes life very easy because of this exponential decay of the contribution of large weight Pauli path. Okay, so so since it decays exponentially, the idea would be compute simply not the entire sum, but truncate it at some weight. And the way that we decide we can truncate it to, we need to truncate it to, is to pick L, this cutoff, as logarithmic in 1 over epsilon, and recall that epsilon is polynomial in the number of samples, m, and so basically L is logarithmic in m or in n, the number of qubits. Okay? So that means that we have reduced the problem to a sum over quasi-polynomially many Pauli path, right? N to the log n. So n choose log n, which is n to the log n, roughly. Okay, so now I want to convince you that really this would work in terms of the contribution to the error, and I want to say that we are actually going to achieve TVD, which is less than epsilon, and we want to upper bound the expectation over the circuits of this delta squared, the total variation distance squared, between the noisy probability distribution and the truncated probability distribution. And basically this uses two properties. The first is anti-concentration again, which will be used by basically showing that the Fourier coefficients, the contribution of Fourier coefficients of large weight is small. And the second is a very important property of this Pauli path representation, which is the orthogonality. So you can see here that the expectation over the product of the Fourier coefficients over different Pauli path is 0. When when the Pauli paths are different, these are 0. So this corresponds to orthogonality. And what this means is actually that basically the interference between the different Pauli paths cancels out when you randomize over the circuits. Okay? And this basically makes life much, much easier because there's no cross terms and no interference. Good. So this follows, the second property of orthogonality basically follows from a result by Aharonov and Law from 2009 that for a high random unitary gate, this quantity, the expectation over high random unitary gates of this quantity where P, Q, R, and S are Pauli operators of 2 qubits, it zeroes out if either P is not equal to R or Q is not equal to S. Basically follows from Schur-Weil duality. So, okay, so I don't want to go into the proof. I don't think we should, it's bad practice, but I just want to show you this part of the proof, the fact that the total variation distance is small by this truncation, just to show that there's nothing to it. Here is the proof. It basically writes down the distance between the two probability distributions, inserts the definition, opens it up, and by orthogonality the cross terms disappear, and then you write it as a sum of decaying factors of the contribution of the Fourier weights on Pauli path with weight k. And the point is that a simple calculation shows that anti-concentration implies this bound. And so we get that the expected total variation distance squared is bounded if we set L to be 1 over gamma log 1 over epsilon. It will be bounded by some function of epsilon. So notice here, you can see here already that so how gamma enters into the exponent that I promised you earlier, because L depends on 1 over gamma, so this is how it enters. Okay, so this is a simple proof, and this is a beautiful, actually the idea, as I said, goes to Gao and Duan. But we're still on quasi-polynomial, and the way to move to polynomial is basically to notice that though we have quasi-polynomially many paths, in fact only polynomially of them contribute to something that is non-zero, and the point is that the reason for that is because polypath, because of the same identity that I showed you before, polypaths that have identity on one side of a unitary gate will have identity also on the other side if they are to contribute something which is non-zero. And so this puts very strong constraints on the polypath that are non-zero, and some we need to work a little bit with some combinatorics, but basically also relying on the fact that this means that the configuration of a layer cannot deviate too much from the previous layer, because you can assume that the weight is small because we've truncated high weight Paulis. And so with small weight, if you start with all identity or with all identity with a single Pauli, in fact, then you can't grow to more than 2 Paulis in the next step. So basically, this really puts a lot of constraints on how the Pauli path, the non-trivial Pauli path work, and we can show that there are only polynomially many of them that really contribute. And each one of the contributions can be easily calculated because the Fourier coefficient for a given Pauli path is easy to calculate because it only involves local gates. Great. Okay, so some assumptions in our main result. What about other models of noise? I've just talked about depolarizing noise. Pauli channel comes for free. What about other models? Well, any type of model with a fixed point being the completely mixed state should work in spirit, but we haven't worked it out. And it's not completely trivial. It requires some work, I think. What about okay? But just to say that this restriction of the fixed point being a completely mixed state is important. We don't expect to be able to do that when the fixed point is, for example, 0, in which you can actually somehow sneak in reset gates into the computation. So this is not something that. So this is important, but this seems to be so some kind of relaxation to the completely mixed state seems to be a reasonable assumption. I want to put a very strong asterisk on that. I think this is something that we keep assuming on our noise model, but maybe we should think about this. But this is a side point. Okay, so what about sublogarithmic depth random circuits? Well, this is unclear even if ideal random circuit sampling is hard. For example, recently this Knapp et al. This Knapp et al. Shows that ideal random circuit sampling in 2D with small depth is classically simulatable. So this is unclear, yet to be studied. What about less randomness in the gates? Again, this is to be studied. We assumed hard random, and in fact, we assume slightly weaker. We assume that the gate set is closed under random Pauli gates. Basically, we need this orthogonality. So it holds for hard random 2-qubit gates or fixed 2-qubit gate plus hard random single-qubit gates. It doesn't yet hold for the Google experiment. So this is still open, and it looks like this is very strong evidence for the fact that that random circuit sampling with a variety of different models will work. But there are lots of examples, of particular examples that you have to go and work through them one by one. We haven't done that. Okay, but still, we think that this is very strong evidence that random circuit sampling is not may not be a good platform for scalable evidence for violation of the extended church Turing thesis. I should say, a very nice paper just appeared a week ago by Bill Pfefferman and friends, O and Jiang and Pfefferman, about sort of a follow-up paper for noisy boson sampling, classical simulations of noisy boson sampling for in certain noise cases. Okay, so it seems like like perhaps this is a good time to start develop new proposals for scalable experimental evaluation of the extended church Turing thesis. And I want to end with a few minutes about the NISQ era in general and with the prospects for doing that. Okay, so the question is, I want to go back to this question of, can we hope for scalable quantum advantage in the NISQ era with other approaches, or what can we hope for? And I want to start with this discussion with the beautiful paper that was presented, I don't remember, was it Tuesday, by Robert, I think? Yeah, right? I don't know, or by Sitan, that initiated the study of the complexity of NISQ. Okay, so they considered, I think it's very important to actually address this question from a computational complexity point of view, and they considered the following model in which you have a quantum circuit with the same model that we're talking about, noisy reset-free quantum circuits with noisy state preparation, noisy unitary gates, unitary, mind you, and noisy measurements at the end. And basically, this already puts some problem. I mean, this already introduces some problem because of this result that says that entropy just grows in such systems. There's no way to pump out entropy, and so the total variation distance from the output distribution to completely uniform, that total variation distance decays exponentially with the depth. So we're basically bounded to log depth if we care to ever distinguish between that and the uniform distribution with polynomial size experiments. Okay, so we're bound to log depth, Q and C, but what they noticed is that very importantly, the right model is not just a single circuit, but the single circuit in the hybrid model of interaction with the classical computer. Okay, so what they defined is this classic problem solvable by BPP with access to noisy quantum circuits without fresh qubits, which you can think of as log-depth quantum circuits, noisy log-depth quantum circuits. Okay, so can we hope for a symptotic quantum advantage with such devices? Taking this as the definition of NISQ devices, which again, I want to put an asterisk on that, maybe, but let's take this as the definition. Well, okay, note, maybe I'll refer to this later in the discussion. So Shor's algorithm is in fact in this model. I made this remark in the first day, but I want to explain this remark. So it's a surprising fact that in fact we have known, though we maybe didn't know that we know, for 20 years. And why is that? So Shor's algorithm is in quasi-NISQ, not exactly in NISQ. And why is that? Well, in 2000, exactly, Cleve and Wattles showed that factoring is doable in BPP with access to log-depth quantum circuits. Not noisy log-depth quantum circuits, but log-depth quantum circuits. However, already in '96, we showed that log-depth quantum circuits can be simulated by noisy quantum circuits of quasi-polynomial size with no fresh qubits, as long as the error rate is below the threshold or some threshold. I want to explain how this proof works because it's very, very simple, assuming fault tolerance. Basically, you start with a fault tolerance construction, say our construction of my construction with Michael Benor from '96 or '97. Can you see this? I lost this. Oh, here it is. So the fault tolerance result, which doesn't require intermediate measurements, but only reset gates. So it requires fresh qubits in the middle because you need to pump out entropy, and this is how you do that. And the map from the ideal circuit to the fault tolerance circuit requires polylog factor in depth. Okay, so now we don't have reset gates, but how do we map actually to a problem with, to a model with no reset gates? Well, the idea is that for every fresh qubit that is needed at time t, prepare exponentially many in t fresh qubits in the beginning of the computation. And just perform noisy majority gates to sort of maintain the quality of this qubit. And this can be done, meaning that if you start from 3 to the t qubits sorry, that are noisy at time 0, you can end up with a single qubit which is as noisy, not much more noisy, at time t, which you can use as a fresh qubit. So this means that you can actually simulate this fault-tolerant computation for log-depth quantum circuit in quasi-NISQ. So you only need, since t is at most polylog, because of the increase in the depth, it's polylog and not log, we only need quasi-polynomially many qubits at the beginning to start with. And that's it. So this means that factoring is in quasi-NISQ, as long as this error rate is below this threshold. And in fact, fault tolerance, if we can do fault tolerance in constant depth overhead, this would put it in NISQ. This is an open question as far as I know. I don't know of any construction with constant depth overhead. But if it exists, I believe it exists, then it is a NISQ. One might wonder, does this actually say that we should try to use Shor's algorithm as our evidence in NISQ devices for scalable violation of the extended Turing? This is not the point. I think the point is really that, I should say, Chen, Kotler, and Huang and Li in their paper also used a similar idea and augmented it with beautiful way of robustifying Simon's problem to show that this problem too is a NISQ eta, in NISQ, not in quasi-NISQ. Again, for eta less than the threshold. But this is not to say that this is a good candidate. Maybe it's to say that we should rethink the definition of what exactly is the problem from a computational complexity point of view, of what is the right model of that we are actually trying to work in. From the point of view of the task of coming up with a scalable evidence for violation. Okay, so to wrap up, basically we could come up with a question of, could violating the extended Turing thesis be demonstrated in NISQ with error above the threshold? This is using a different idea. Could this be done with quantum simulations? Trying to attack the Goldreich-Sudan challenge. And I should mention the beautiful paper, the best student paper that won last night, the best student paper award, about the energy states of sparse random Hamiltonians. Perhaps this could lead to such a candidate for quantum supremacy. And I want to take the advice of Harry Borman's last words in his in the speech yesterday, and end with a question: have we probed the high complexity regime of quantum mechanics so far? I think, given all this this discussion, probably not. Thanks.
That's enough. You mentioned in passing a similar result to the here. Yep. You mentioned in passing a similar result to the main one that you're presenting, where other people do the same thing with Gaussian boson sampling. So how does this framework that you're presenting compare to the earlier sort of similar sounding result of Kalai and Kindler?
Yeah, maybe, I don't know if, actually, don't really know this paper very well because it just came out a week ago, but maybe I'll let Bill answer this. Do you want to answer this?
Yeah. Okay. Sorry, do you hear me?
Yeah.
Okay. Yeah, so Kalai and Kindler is talking about exactly the same noise model that we're talking about in our algorithm. It's some sort of Gaussian noise model, but they're only talking about a noise model that allows them to compute probabilities. And there's sort of a technical difference between computing full output probabilities of a distribution and sampling. And so in our new work, we show how to do both of these for the noise model that Kalai and Kindler talked about. One additional thing I'll say, though, is that there are other noise models that are actually more physically relevant for boson sampling, like photon loss in particular. And interestingly, we don't know how to adapt this sort of algorithm in those cases. So I think that's still a big open question.
Hi. Thanks for the really nice talk. I have two questions. So one is there any fundamental limitation on how the algorithm could be improved, like the scaling of gamma? And maybe, I don't know, maybe you could consider like gamma like little low of 1, and I mean, that could lead to like lower bounds probably. And the other question is with regard to the complexity of NISQ. I think if we add in spatial locality, which would then truly model NISQ.
I'm sorry, if you add what?
Spatial locality, which would then model truly NISQ devices, do we still expect some sort of speed up even if the noise rate is like below some threshold?
Right. These are two excellent questions. First of all, about the 1 over gamma, the particular approach that I've showed is not going to work below 1 over gamma. Whether or not this can be improved, I don't know. Working on this, I don't know. About the 2D restriction, this is a very good point. Of course, in ions, this is maybe not the right restriction, but in superconducting qubits, it is. And it seems like it might be, so attempting to actually make NISQ definition more NISQ-y, maybe one can think of really making it 2D. Maybe one can think of making the noise larger than the threshold. You're asking whether in 2D one can hope to derive such advantages like Shor's algorithm, even if eta is less than the threshold. Well, we don't know that for this particular algorithm, but I want to say that it's not on the face of it ruled out. You could think that the light cone argument of having a quantum circuit in 2D means that if you have a deterministic answer, you only need to calculate the light cone, which is just polylog qubits. But in fact, in these algorithms, you don't have a deterministic answer. You have a sampling problem. So then that might actually work, and I don't know the answer. It's a good question.
So maybe a last question.
So, thank you for your talk. The path interval trick is very nice, so congratulations for that. My question is about how you decide how you define that you are sampling from the closed distribution, like this epsilon that you use. So you could reproduce the same argument for the uniform distribution, right? Like if I take the uniform distribution, I could just say, oh, I sample epsilon closed, and you could kind of reproduce a similar argument. So what is
a similar argument for what? For simulating?
So yeah, so I could come with a similar argument. So and your algorithm is much more subtle than that. So what is the subtle? So I'm not sure whether this using the total variation distance is like the right maybe target goal. Like will it change your scaling if you use the cross-linear entropy, for example? If I want to have a cross-linear entropy of a given value.
I think you're referring. Okay, time is running backwards.
Yeah, this exactly that slide. So could you? I have the impression
I think I'm going to this slide. No, So I think you're asking, if I'm not mistaken, you're asking on the fact that since uniform and the output probability distribution are inverse polynomial closed, Why is that? How can we ever make a test that will distinguish between the output of a noisy quantum circuit and classical? Right? Because in any case, it's uniform, it's close to uniform. But the point is that we're talking about inverse polynomial, which is even smaller than the inverse polynomial that we're talking about something inside this window. I don't know why I cannot see this, and suddenly it appears. Okay. Yeah. So this is the uniform, and this is the noisy random circuit sampling, and we're talking about approaching this value much smaller than this window, though still inverse polynomial. So we still have the resolution that's good enough.
Okay.
Okay, so we have to stop. Thanks again, Dorit.